Yay!
Yay!
Hello. This is a cool problem, a nice example I've seen in basically every textbook I've ever taught out of. It's kind of a neat example of conservation of energy and how to design things like roller coasters. So here's the idea. I have a little cart up on a hill, and it's like H above the ground. And then I want this thing to go down and go around a loop. And the constraint is that I want people to live. So when it gets to the top of the loop, I don't want it to come off the track. Because you know from what we did earlier with centripetal motion, if it goes fast enough, it'll stay on the tracks all the way around. The normal force will be greater than zero right at the top. So this thing will stay on the tracks and it'll be a thrilling ride, but we want people to live, so we don't want it to come off the tracks at the top. If it goes too slowly, it won't make it all the way around that loop. So where does the speed come from? It comes from that height h. Assume no friction. There's no friction anywhere. So how high does h have to be so that it makes it around the loop? It turns out it'll just be a function of how big the loop is, r, the radius of the loop. So let's figure it out. So again, here we go. Initial energy is going to be equal to the final energy. And the two places where I want to look at the energy are at the very beginning. And what's happening at the very beginning? There's no springs. It's at rest. We're just starting from rest at the top of the hill. So the only thing we've got at the beginning is just mgh. And then at the end, now this where we want to examine the energy is at the top of that loop. Let's see what the energy is at the top of the loop. At the top of the loop, does it have potential energy? Sure, because it's some height off the ground. How high is it off the ground? 2r, right? The diameter. So this is going to be mg times 2r is going to be its potential energy at that point. And hopefully it's going to be moving, right? It'll have some kinetic if the people are going to live. So this is going to be 1/2 mv squared at that point. Okay, well, you can see right away, thank goodness, if we're designing this ride, all the masses cancel. So it doesn't matter how heavy the cart is. That's a sigh of relief. So it doesn't matter if the cart is empty or full or who's in the cart, right? Mass doesn't make any difference. That's nice. Look at that V though. What is that V going to be? It's going around the loop, right? So go back and think about if this cart, let me draw a bigger picture of this thing. If this cart is going around the loop, those are cartoon motion lines. If it's going around the loop, what are the forces as it's going around the loop upside down like this? Well, if it's going to stay on the track, we've got a normal force going down, right? Gravity is trying to pull it down. That's it. That's all I got. So what we have was, and this is very much like sort of our Ferris wheel that we did before. I've got n is going down, mg is going down, and this equals to how it's accelerating. Well, it's going around in a circle. So it's centripetal acceleration, and the center of the circle is also down. So it gets a minus mv squared over r. So all those minus signs go away. And what's the critical point we're interested in? What we want is things start getting dangerous when it comes off the tracks. As long as there's some normal force, we're going to be okay. But when n goes to 0 is the critical case we're interested in. And that depends on the speed, right? That depends on that v. So when the normal force is 0, it's just starting to come off those tracks, which is no good. And when does that occur? I can cancel out, again, the masses cancel. So v is, I guess we're calling it a capital R, right? So v is rg. In order to stay on the tracks, is what we're saying, it has to be traveling with that speed v, or else it'll come off. So look, now I can plug that in right there, because that's our condition, that it stays on the track. So what we have is GH is equal to 2RG plus 1/2 V squared. Well, that's just RG. Look at that. And look, all the G's cancel. That's kind of neat. What that tells you is, we haven't really talked about this much yet, but G is just the acceleration of gravity on the Earth. So it turns out you're all set for the moon economy. If you want to design this roller coaster on the moon, you're good, because it doesn't depend on the local gravitational acceleration. Everything is fine. So look, we're done. I can solve for my H. H is just 2r plus a half r. That's going to be 5/2 r. Very cool. So as long as, or 2.5 times r, right? So as long as my starting height is greater than, let me just put in that condition, as long as my starting height is greater than or equal to 5/2 r, then I'm going to make it. This is going to be a safe ride, at least with the considerations we have so far. No friction and all that, right? Which isn't ever true in the real world. But again, this is an idealized thing just to get an idea of how much this has to be. So this is an example of energy conservation with a constraint of going around a circle at the end. But this is sort of a neat problem illustrating design. Cool.